All right, and now we're going to start our next session. I had a slide that was going to introduce Julia, but as I said, we're figuring out this platform, so Julia has her slides up already, which is great. We're very excited to have Julia Lassarre here, who is from Zalando, and she has an interesting background that I hope she mentions briefly to introduce herself. And the talk will be about how to make sure that customers have best match their unique sizes and fit preferences. Am I right?
Yeah, thanks, Galina. Hi, everybody. Yeah, I'm Julia, and I work at Zalando. If you don't know it, Zalando is an e-commerce fashion platform. So we sell clothes, shoes, beauty, accessories, and so on, all across Europe. We are not, yeah. My background is very shortly because it was mentioned. I did a PhD in machine learning and worked on computer vision for a bit. Then did a postdoc in bioinformatics and decided to join the industry. And I started in the industry with Zalando, and I'm still there. And that's one of the things that I really like about machine learning, that you can see a lot of different applications, and there's really no limit to how many domains it can be used in. All right, so in this talk, I will discuss personalized size recommendations based on purchase history. And let me first maybe give you some context why we would do such a thing. So sizes are really complicated, much more than we would imagine. So maybe if you are a keen shopper, it has occurred to you already. There are various problems that lead to this, to the difficult topic of finding a size. The first problem is that it's mass production. So we don't have so many tailors anymore. It used to be handmade for people, but now we all get the same sizes, and these sizes are manufactured far away with sets of dimensions that are not necessarily up to date or not necessarily specific to the market in question. There are also no uniform sizing conventions. So if you go from country to country, it's different. But not only country to country, also within brands. And within brands, even from category to category. So t-shirts might not be sized the same as trousers. There's also the problem of vanity sizing, which is that brands basically try to please their target audience. And if it's a brand for young people, maybe sizes tend to be a little smaller. And if it's for maybe more classic, the sizing will be different and a bit bigger. And also, finally, there are multi-dimensions to sizing. So if you think about trousers, for example, you have the waist, and the length. There are also all the fit dimensions. So whether you like it tight or whether you like it more loose, or and all of this makes it really difficult for customers to pick their size. And you go online, you see thousands of products, and you have no idea. Maybe even if you're an average size, that could be a S, that could be a M, that could be a L. Average size means different things in different brands. So this is an opportunity for Zalando, of course, because this problem leads to many returns. So roughly half the items that are sold are returned, and about 40% of these returns are size related. So you can imagine that it's quite an opportunity in terms of costs and in terms of also selling products. And all these returns are also not the greatest thing in terms of environmental considerations. For a platform like Zalando, there are many challenges. So related to size and fit, and some are on the article side and some on the customer side. And on the article side, as we saw, we have different size systems, so no conventions. We also have new articles where we have no sales or no returns. We have ambiguity or low quality of fit data. So we don't really know, even if the brand says, slim, it could be skinny in a different brand, or it could be regular. So every brand has their own thing. And there's also a delayed feedback due to return process. So to see if an article has a problem, it may take 3 weeks or, On the customer side, of course, we have the typical challenges that many platforms have. So we have multiple customers behind one account. So for example, Netflix solved that by having profiles. And we have also data sparsity and new customers. So new customers come on the platform all the time, and we don't have purchase history from them. And we have also different customers having different willingness to give data, right? So customers have their own personal preferences as to what they want to share with us, and we have to compose with that. And finally, we would like also to engage in a dialogue with customers. So when it comes to size and fit, it's a highly emotional topic. Expectations can be quite high, and it's very difficult to tell a customer what size we think they are. That is, that can be very sensitive. So we also have the challenge of explainability. So all of this means that we've developed a size and fit organization at Zalando, which is now a very big team. And it's a very multidisciplinary topic. So we have various components to this size and fit organization. I work personally on the bottom left in the data science and research engineering part, but we also have, of course, software engineering, product design, business analytics. And what we have also is R&D engineering, where we work on 3D data. And we also have fitting models and assistants. So there are models at Zalando who are maybe size medium and who try clothes on and say whether it's too big or too small and measure them and so on. So we can also use this data inside our algorithms. But today I want to talk specifically about our product Size Reco. So if you are a shopper at Zalando, you might recognize this. So this is a typical product page. And you can see images of the product. And here you will see, we say we recommend size 30 times 32. And this is what we mean with the product size recommendation. So this assumes, of course, the user is logged in. So to talk about a size recommender, maybe we could set a set of targets. So in an ideal world, what would the recommender do? Well, it would perform well on metrics of interest, whichever your metrics are. It should naturally handle the various existing size systems. So we have many sizes. As an idea, I can tell you, if you look at the strings themselves, so if you treat a size as a basic string, set of characters, it's counted in thousands. So we have about more than 2,000 sizes. And two different strings can mean the same size, and the same string can mean different sizes, or can be declined in different sizes depending on the category. So yeah, this is, and of course, various size systems coexist in there. It should also handle customer or article metadata. So if we have additional information about the customer or the article, it would be nice to be able to put it in. It should also adapt to new customers without having to retrain all the time. And leverage cross-category information. What do I mean by that? I mean that if you shop 10 times for t-shirts, then it would be nice after a while to imagine what your lower body might look like. So if you're size M in t-shirts, chances are you're not going to be size XXS in your lower body. So we can start making inference from category to other categories. It should handle multi-user accounts, and it should be interpretable. So currently the main production algorithm based on purchase history is a simple baseline, which works really well, actually. So it's basically a customer size distribution, which comes from the purchase history. I won't talk so much about this algorithm, but just to give you the idea, it's so the purchase history of the customer gives a baseline distribution that we can see in blue. And then we have information about the article based on returns and so on, purchases and returns, which gives us an idea of whether the article tends to be small or big compared to what's expected. And this means that we can adjust the customer size distribution with that information, leading to the green distribution. Once you have a distribution like this, you can say, okay, the most likely size is going to be 43. Yeah, that's roughly quickly how the main production algorithm works. But this algorithm has a set of issues. So if we measure it against our targets, it doesn't naturally handle the various existing size systems. The main reason is that because we are looking at such numerical distributions, then sizes have to be converted. And for this, we need experts. So it's a lot of expert work. It's very difficult to add any sort of meta information about articles or customers. And because sizes have to be converted, this is done on a category level. So there's also no information between categories. And there's also no interpretability. Okay, and now I want to get into the meat of it. Yeah, I want to talk about MetaLSF, which is our size recommender based on meta learning. Yes, meta learning, you might be very familiar with it, but this is something that started with ImageNet. Well, maybe not started, but that gained popularity with ImageNet. And the concept is that if you're presented with many tasks, you should be better at solving tasks, right? So if the tasks are similar, if they have a component that ties them together, then it shouldn't be the case that you solve each task individually. At some point, you should also learn how to solve these tasks more efficiently. And so in this case, for example, we have images, and each task is like a binary classification here. So on the first row, we have dog or no dog, and the second cliff or no cliff. And if we train a meta learner to solve these tasks together, so not independently, so not having a separate model for each, but having a joint model. Well, a joint meta model. The model itself might be separate, but the joint meta model. And then it should be easier when we have a new task, lion versus no lion, for example, to learn it. And by easier, it means that you should need fewer examples. I mean, that's one of the targets for easier. So what does it mean for size recommendation? Well, in this case, we will treat a task. So instead of lion or no lion, we will treat a task as a customer, and where the images are now replaced by their purchases. And so for a particular task, we will have samples, tuples X and Y, where X is the article that is purchased by the customer, and Y is the size that it was purchased in. And we will call the historical purchases of the customer a support set. So that is what we will use to give information about the customer. And the query set will be the set of purchases of the customer that we use to test. So every time you get customer's purchase history is divided in two: the support set that we use to inform the model, and the query set that we use to test. This is basically the model that we put together. So let me get into it a little bit. So what happens is that here we have X1, X2, X3 in black, which are historical purchases. So X is the article, and here we have the counterpart, which are the historical sizes that were bought for these articles. This is for one customer, by the way, what we are looking at. And this is what happens for one customer. And These articles are encoded via some network here, f of x. And as a result, they live here in an embedded space where we have x tilde 1, x tilde 2, x tilde 3. And the same for sizes. Sizes are encoded in some embedding space. And we have here y tilde 1, 2, 3. What this means is that we now have a virtual space, or like a latent space, if you will, where we have the three historical purchases live. We can see the black dots, and we're going to fit a line out of these black dots. So we have embedded linear regression there. And now when we have new articles, so x4 or x5, so x1, x2, x3 is our support set, and now x4 and x5 are new articles we want to make inference on, our query set. We also embed these articles through the encoder here, and we get two blue dots here, and two blue entries here. And thanks to the line, we can predict the y-axis. But of course, the y-axis is still in embedded space. So here we predict an encoded size. And now we need a decoder, which brings that size back to a distribution over actual sizes. Yeah, so there are three main components in this model. So the encoder, the article encoder, the size encoder, and the size decoder. And there is also the embedded linear regression. And what happens is that as you add customers and customers and customers and customers, the encoders are always shared. So they learn how to basically create a space where tasks are easily solved. So now for the next customer, we have the right encodings and we can solve the task easily in linear space. It's very similar in the idea to kernels. Yeah, so this is basically the model. And the regression, the embedded linear regression, is actually rich regression. The reason is that here I pictured it in one dimension, but so x and y are both unidimensional, but in reality, it's not the case. X, I think x is 128 dimensions, I think, and it's really rare that we have enough historical purchases to have a well-defined problem. So in practice, we regularize and we do rich regression with the parameter lambda. And this lambda is learned as part of the model. But otherwise, it's standard rich regression. And so we learn a set of weights, and then we can make a prediction for the query articles using standard regression. The set of weights, you can see this as the summary of the customer, because the set of weights summarizes the purchase history of, the support purchases of the customer, the black dots. Okay, I want to show some results on this model. But first, I want to describe shortly the data. The data we use for this is basically articles that are purchased and kept by customers together with their selected sizes. And then we have a few attributes like brand, category, material, season, etc. Purchase data, you have to think, is very sparse. Few customers buy each article, and or very few. And especially when you combine this with sizes. So with sizes, it's even more sparse. And this is the data that we used. 10 million purchases and 400,000 customers. This was in the paper. In the meantime, we have increased the data set, and you can see that, this is a distribution of the number of kept articles per customer, and most customers have few, maybe 5 articles or something like this. Okay. In general, when you do meta learning, what happens is that you would have a set of customers for training and a set of customers for testing. This is not really what happens here because our product doesn't work this way. So we are a platform, right? People come and go. And so what we do here is not a split by customer, but a split by time. So we train on past data and we test on new data, basically. So it's okay that the customer was already seen, as long as we don't test on the training purchases. So as long as we don't use the training purchases in testing. So it is a use case for us that customers come back. That's actually precisely the use case we want to solve, right? That customers come back, they are not entirely new. And we want to use their past data to make inference on future data. So for training, we look at training purchases and we split them between support and query. For validating, the support purchases will be the training purchases and the query will be the validation purchases. And for testing, we don't need to go into the scenarios, but for testing, the support purchases will be, again, the training purchases, and the query will be the test purchases. Yeah, so I don't really have time to go into all the models here, but the main message here is that it's to give you an idea of the performance we get with MetaLSF. So MetaLSF is the model that I presented. So top one accuracy is basically how often do you recommend the size that was picked by the customer? About 60% of the time. Top two is, how often do you pick, how often does the size picked by the customer fall into your top two recommendations, and top three, and so on. So these are typical numbers inside recommendation. Here we have a plot which shows accuracy versus coverage. Coverage means, so this is relative coverage. This means out of all the test purchases that we had, where MetaLSF could make a prediction, how many did we actually make a prediction on? And of course, if you have no threshold on the probability, then you make a prediction on all of them. But if you start saying, oh, okay, but it was with probability 0.3, that's not so great. Let's have at least probability 0.4. Then you reduce coverage, but you increase potentially accuracy. So what happens here is that we moved the threshold from 0 to 1 and built this curve where as you increase the threshold, you reduce coverage, but you increase accuracy. And you can see this curve for all the models. And MetaLSF would be here at the top. So this means that for equal coverage, we would have higher accuracy. Yeah. Sorry, I'm over time, I think, or no, 1 minute. So I also wanted to show briefly that because all categories are now put together, so MetaLSF is not working in numerical space for sizes anymore. It is treating each size as a categorical value. And thanks to this, we can put all categories together. And this means that as we learn what customers buy together, we start learning what is the distribution. So if you're top size M, what is the distribution of sizes for the bottom? And here we did, so can you predict upper garments if the customer has no purchase history in upper garments? And this is the best guess. If we didn't have any information, we would predict the most common size, which would be here 0.3 accuracy. And we are a little better, 0.4. It's far away from the 0.6 we get with purchase history, but it's still a little better. And for lower garments, it also works better. So can we predict lower garment sizes without any information? Without any prior purchases. Okay. I wanted to say also that thanks to the linear regression, so you can check the math in the paper, but what happens is that we can give a score to each of the support purchases that led to the decision of the size prediction. And this means here that, for example, for this query article, this would be the typical size prediction distribution we would have. And then we would have scores on each of the support set. So for example, here the stop is the closest, it's 0.36, the coefficient, and for shoes it's 0.0 something. So from there it's about 0. So basically it looks at upper garments, and particularly this top, I think, because it's the same brand. And it also works if you have new categories. So this skirt, for example, the customer had no skirts in their purchase history, but given the dress and given the dresses, it was fine. You will notice that this dress is not size 40, it's size 50. It's a different size system, but it still figured it out. Okay. However, these weights have an issue of their own. They're not always bound, so they can go between -1 and 1. They are not always positive, and they're not always bound. There are some issues with the theory. So we have been working subsequently on attention models to get actually weights that are more easily interpretable and that are more behaved. Okay, and I just want to say that we made progress basically on our targets, and particularly handling the various existing size systems. So we can now do this much better. It's not yet perfect because, of course, as you train, you can only predict what you have seen. So if we have new sizes, then we need to retrain. But still, we don't need to convert sizes anymore, and we can have as many sizes as we need. Okay, then I will, and also we can leverage cross-category information, which we couldn't before.
So we have only a few minutes left for questions, Julia.
So and let's go for question. Yeah.
Yeah. First, thank you very much for the talk. This was very interesting and very practical also, as I think many of us are doing purchases online these days. And then this is the first test of the Q&A system that we are doing here. And the first question is, how often do you update your model once you get more and more data every day, week, or month? And have you seen a big change in the model predictions after updating it?
Thanks for the great question. So actually, we don't update the model so often, because what happens is that once the encoders and decoders are trained, what we do is that we update the purchase history of the customer. So every day we pass the customer purchase history through the model to update the customer these weights that I showed in the linear regression. Those weights are different because we add more and more points in the latent space as the customer buys more and more. But the model itself doesn't need to be trained so often. So for example, there is barely any difference in 3 months or even in 6. So what matters a lot, but there is a big difference, however, so the encoders don't need to be retrained, but it's very important to update the customer purchase history. So to recompute the linear regression.
So we have a minute. How about we go quickly through the rest of the questions? Because I think they're all kind of interesting. Yeah. They get at something related to how this is done. Would it be okay, Julia?
Yeah, sure.
So we have one from Emily Bergström. So how long historical data do you take to predict the model? Are you taking entire history of the data, or do you have like X recent purchases?
Most of the time we take the entire history. So it can be 1 purchase or it can be 200. So that's fine. We are flexible with this. The only thing we do is if it looks like too many purchases, it's probably resellers. So we discard them from training.
Makes sense. And Luminita is asking whether you're predicting only one size per customer.
Yeah, so right now we predict 1 size per customer, and there is work being done on uncertainty and how to deal with that. But currently in the product, we predict 1 size per customer. And if we don't have a size available that fits them, we don't predict anything. So we don't recommend anything.
Makes sense. And the last question, are there different size models on a per brand basis, or is size assumed to be uniform across brands?
So size is not uniform across brands, but we do hope that with the encoders, because brand is part of the attributes. So brand and category are part of the attributes. So the encoders sort of organize the space where sizes can be compared. So yeah, this also happens between across categories, for example.
Yeah, makes sense. Julia, thank you very much.